A dead star's heartbeat echoes across 50,000 light-years. This is the pulse of a magnetar, the universe's ultimate cosmic monster and the most powerful magnet in existence. By the end of this journey, you will understand forces so extreme they warp reality itself. We will confront starquakes that outshine the sun and unravel the mystery of bursts that can be felt from another galaxy. What does true cosmic power look like when it is unleashed? To grasp the sheer scale of that power, we need to understand what we are dealing with. A magnetar is not just any dead star. It is a specific kind of neutron star, the final, furious ember of a giant. Picture a star many times more massive than our own sun. After it burns through its fuel, it explodes in a cataclysmic supernova, blasting its outer layers into space. What remains is the collapsed core, crushed by its own immense gravity into an object of almost impossible density. This is a neutron star. If you could scoop up a single sugar cube's worth of its material, it would weigh as much as an entire mountain, like Everest squeezed into a tiny block. Now imagine taking this cosmic cinder and cranking its magnetic field to an insane, universe-bending extreme. That is a magnetar. While all neutron stars have powerful magnetism, magnetars are the rare, monstrous outliers. They are typically about 20 kilometers across, yet they pack more mass than our entire sun. They spin rapidly, completing a revolution in mere seconds. But their defining feature, their terrifying signature, is their magnetic field. It is a quadrillion times stronger than the Earth's. To put a quadrillion in perspective, that is a 1 followed by 15 zeros, 1,000 trillion. This is not just a strong magnet. This is a force so potent it warps the very fabric of space around it. This monstrous magnetic field is forged in a single, spectacular act of violence. The story of a magnetar begins not with a quiet fading, but with the most energetic explosion in the modern universe, a core collapse supernova. It requires a star at least 8 to 10 times more massive than our sun. For millions of years, this giant burns through its nuclear fuel, fusing lighter elements into heavier ones in its core. It is a layered cosmic onion with hydrogen on the outside and iron building up at the very center. Iron is the ash of stellar fusion, a dead end. It cannot release energy by fusing further, it only consumes it. So when the iron core grows too large, the star's internal support system fails catastrophically. In less than a second, gravity wins. The core, which can be as massive as our entire sun, implodes. It collapses inward at nearly a quarter the speed of light. The outer layers of the star, now unsupported, come crashing down after it, only to rebound off the newly formed, incredibly dense core. This rebound triggers a titanic shockwave that rips the star apart from the inside out. The resulting supernova explosion can outshine an entire galaxy for weeks, blasting the star's outer layers into space in a beautiful, expanding cloud of gas and dust we call a supernova remnant, like the famous Crab Nebula. But the true drama is in the collapsing heart. That imploding core, crushed to unimaginable density, becomes a neutron star. For most neutron stars, that is the end of the story. But to create a magnetar, something extra is required in that chaotic forge. During that frantic moment of collapse, if the original star was spinning very rapidly and its core was a particular superheated soup of particles, a dynamo effect kicks in. It is like taking the magnetic field of the original star and winding it up trillions of times tighter as everything is compressed. The newborn neutron star's magnetic field becomes so concentrated, so amplified, that it crosses the threshold into monstrosity. In that instant, amidst the stellar wreckage, a magnetar is born. That magnetic field is a number so large it loses all meaning. We must translate it into a language of consequences. The strength of a magnetic field is measured in a unit called Gauss. The gentle field that guides a compass needle on Earth measures about half a Gauss. A common refrigerator magnet is about 100 Gauss. The most powerful magnets we can build in laboratories using superconducting coils can reach hundreds of thousands of Gauss. Now hold that thought. A typical magnetar's magnetic field clocks in at around 10 to the power of 15 Gauss. That is 1 quadrillion Gauss. If you could bring a magnetar halfway to the moon, its magnetic influence would still be powerful enough to erase the magnetic strip on every single credit card back here on Earth. It is an utterly incomprehensible force at a cosmic distance, but how do we even know this number? We cannot travel to a magnetar and take a reading with some celestial multimeter. Astronomers measure this immeasurable force through its fingerprints on the radiation the star emits. One key method involves watching the magnetar spin. All neutron stars are born spinning furiously, but their intense magnetic fields act like brakes, radiating energy away and causing the star to slow down very gradually. This is called spin down. For a magnetar, that braking effect is astronomically powerful. By precisely timing the star's pulses of radiation and measuring how much its spin slows over months or years, scientists can calculate the strength of the magnetic field causing that slowdown. It is like figuring out how strong a wind is by watching how quickly it slows a spinning top. Another method comes from the X-rays themselves. The twisted, snapping magnetic field lines trap a dense atmosphere of particles around the star. When these field lines rupture and reconnect, they accelerate these particles to nearly the speed of light. The energy released in these events is so specific and so tremendous that by analyzing the exact X-ray signature, researchers can deduce the intensity of the magnetic field that must have been involved to create it. These indirect measurements paint a consistent and terrifying picture, confirming that we are observing objects where magnetism ceases to be a simple force and becomes a dominant feature of reality. This unimaginable force is not a static cage, it is a living, writhing entity, and when it moves, the very star itself can shatter. The surface of a magnetar is not a fluid ocean of fire like our sun, it is a solid crust. Picture a shell of iron, but an iron forged under pressures that make diamond feel like tissue paper. This crust is crystalline, perhaps only a kilometer thick, yet it is harder than any material we could ever conceive. Beneath it, the interior of the magnetar is a superfluid, a frictionless quantum liquid of neutrons. And running through it all, like steel cables twisted to their breaking point, are the magnetic field lines frozen into the star's structure during its birth. Here lies the recipe for cosmic violence. The interior of the star, that superfluid, can rotate slightly faster than the rigid crust above it. This differential motion stretches and twists those embedded magnetic field lines, storing titanic amounts of energy, like winding a spring made of space-time. The solid iron crust is forced to contort under this unbearable strain. It bends, it warps, it builds up stress until it can hold no more, and then it cracks. This is a starquake. It is the seismic rupture of a celestial body, but to call it an earthquake is like comparing a firecracker to a supernova. When a magnetar's crust fractures, it does not just shake, it releases a cataclysm. In a fraction of a second, the crust shifts by perhaps just a centimeter, but that tiny movement under these impossible conditions unleashes more energy than our sun radiates across 100,000 years. The entire star rings like a bell, oscillating violently. The snapping of the crust injects a massive surge of energy into the magnetic field, causing it to reconfigure in an instant. This triggers a colossal flare of X-rays and gamma rays, a burst so bright it can temporarily blind satellites pointed in its direction from across the galaxy. We are witnessing a star literally breaking its own bones, and the scream of that fracture echoes across the cosmos as a pulse of pure, annihilating light. The scream of that fracture is a giant flare. When the magnetar's crust shifts, it violently shakes the entire lattice of magnetic field lines anchored within it. Think of it as grabbing a handful of taut rubber bands and yanking them sideways. The stress becomes too much and the bands snap. On a magnetar, these are not rubber bands, they are conduits of pure magnetic energy. As they break, they whip around at relativistic speeds and then violently reconnect, slamming together in a process known as magnetic reconnection. We see a much weaker version of this on our own sun, where reconnecting field lines cause solar flares. But here, the scale is beyond comparison. The energy released in that single reconnection event dwarfs the total output of our sun for 100,000 years, all focused into a flash of radiation lasting barely a tenth of a second. This is a giant flare, an explosion of gamma rays and X-rays so intense it can outshine every other source in the gamma-ray sky for that fleeting moment. The power is not theoretical. On December 27, 2004, a magnetar named SGR 180620, located about 50,000 light-years away in the constellation Sagittarius, did exactly this. It unleashed a giant flare. For 0.2 of a second, it was the brightest object ever detected outside our solar system in any wavelength. The radiation pulse, traveling for 50 millennia, finally washed over our solar system. It was so powerful that it actually ionized the upper layers of Earth's atmosphere, distorting long-range radio communications and causing our planet's ionosphere to briefly swell. An object halfway across the Milky Way galaxy reached out and physically touched our atmosphere. That is the reach of a magnetar's fury. That brief, blinding flash is the unmistakable signature of a monster. But not every dead star that pulses is a magnetar. The cosmos is filled with spinning neutron stars we call pulsars, their lighthouse beams of radiation sweeping past Earth with metronomic precision. So how do we tell the difference between a regular pulsar and a magnetic leviathan? The distinction lies in the source of their power and the rhythm of their pulse. All magnetars are neutron stars and many neutron stars are pulsars, but not all pulsars are magnetars. Think of it like engines. A typical pulsar, especially the fast-spinning millisecond variety, is powered by its rotation. It is a cosmic flywheel, beaming out energy as its spin gradually slows down over eons. Its magnetic field, while still immensely strong, is thousands of times weaker than a magnetar's. A magnetar, however, is powered by the decay of its own monstrous magnetic field. That twisting, stressed magnetic field is the battery, and its slow, agonizing relaxation is what fuels the star's intense X-ray glow and its catastrophic outburst. This fundamental difference in engine design shows up in their behavior. Look at their spin. Many pulsars are speed demons, whirling hundreds of times per second. A magnetar, weighed down by the sheer density of its own magnetic energy, spins far more slowly, typically completing a rotation once every 2 to 10 seconds. It is a sluggish, heavy giant compared to the buzzing hummingbird of a millisecond pulsar. Now look at their light. The radio beams from a typical pulsar are steady and predictable, like a perfectly timed strobe light. A magnetar's X-ray emission is different. It is erratic, simmering with a constant low glow from its hot, magnetically heated surface, and then occasionally erupting into those violent flares and bursts. Its light curve, the graph of its brightness over time, looks not like a clean pulse, but like a restless, spiky heartbeat punctuated by catastrophic spikes. So when astronomers detect a new spinning neutron star, they ask a series of questions. How fast does it spin? What kind of light is it emitting, and how steady is that emission? Is it showing any signs of explosive activity? The answers paint a portrait, revealing whether they have found a relatively stable celestial lighthouse or a slumbering magnetic titan, its crust groaning under unimaginable strain. The true horror of a magnetar is not just in its distant flares, but in the permanent nightmare that surrounds it. This is a place where the very rules of chemistry and physics are rewritten by force. Within a bubble of space stretching roughly 1,000 kilometers from the star's surface, the magnetic field is so overwhelmingly powerful that it does not just attract metal, it reshapes reality at the atomic level. Picture an atom with its nucleus orbited by a cloud of electrons. In this environment, the magnetic force is billions of times stronger than the electrical force that holds the atom together. The result is catastrophic. The atom is violently stretched, its spherical electron cloud warped into an impossibly long, thin cylinder. The atom ceases to be an atom as we know it. Any matter that ventured into this zone, whether the hull of a starship or the fragile body of an astronaut, would undergo instant and total annihilation. The magnetic field would rip every single electron away from its atomic nucleus in a fraction of a nanosecond. Organic material would not just melt or vaporize, it would be deconstructed into its fundamental particles, a cloud of bare atomic nuclei and free electrons. You would not just die, you would cease to exist as a coherent structure. This lethal magnetic sphere is just the first layer of defense. Even if you could somehow survive that, you would then face a constant, torrential downpour of death from the sky. The Magnetar's surface, heated to millions of degrees by the decaying magnetic field, glows fiercely in X-rays. The space around it is filled with a permanent, seething fog of radiation, a product of particles trapped and accelerated by those twisted field lines. To be near a magnetar is to be bathed in a light that does not illuminate but obliterates. The X-ray and gamma-ray flux is so intense it would deliver a lethal dose to an unshielded human in milliseconds and would fry the electronics of any probe long before it reached that fatal magnetic boundary. This is not a place for exploration. It is a cosmic kill zone, a neighborhood where the very fabric of matter is torn apart and space itself crackles with invisible, annihilating fire. On March 5, 1979, the universe screamed. Without warning, a flash of gamma radiation of unprecedented intensity washed over the solar system. It was so powerful it saturated the detectors on 9 different spacecraft, from American Vela satellites to Soviet probes, all designed to monitor for nuclear tests in space. For a terrifying fraction of a second, the instruments went blind, overwhelmed by a signal that dwarfed anything ever recorded. This was not a whisper from the cosmos, it was a deafening roar. The source was quickly triangulated. It came not from within our own galaxy, but from far beyond, originating in the Large Magellanic Cloud, a satellite galaxy of the Milky Way 160,000 light-years away. For a burst to be that bright from such a staggering distance meant the energy released was almost beyond comprehension, equivalent to the total energy output of our Sun over 1,000 years, unleashed in a single instant. But the mystery only deepened in the aftermath. The initial blinding spike of gamma rays faded, but it did not disappear. Instead, it gave way to a rapidly fading tail of radiation that pulsed with a perfect rhythmic beat. Every 8 seconds, like the ticking of a cosmic clock, a pulse of softer gamma rays arrived. This was utterly bizarre. Gamma-ray bursts were thought to be one-off cataclysms, the final death cries of massive stars or collisions of neutron stars. They were not supposed to have a steady, periodic heartbeat afterward. The 8-second pulsations continued for minutes, slowly fading into the background noise of space. Scientists were completely baffled. What kind of object could produce such an initial explosion and then settle into such a precise, rapid pulsation? The leading theories of the time strained to explain it. A black hole? No, black holes do not have a solid surface to pulse. A regular neutron star, its magnetic field was thought to be far too weak to power such an extreme outburst. The event, catalogued as GRB 790325, became a legendary puzzle in astrophysics. It sat in the scientific literature for over a decade, an anomaly waiting for an explanation. The answer finally came in 1992 from theorists Robert Duncan and Christopher Thompson. They revisited the data and proposed a radical new class of object, one powered not by rotation or accretion, but by the decay of an unimaginably strong magnetic field. They calculated that a neutron star with a magnetic field strength of around 10 to the power of 15 Gauss could explain everything about that 1979 event. The initial giant flare was the star quake, the catastrophic snapping of the Magnetar's crust. The subsequent 8-second pulsations were the dead star itself, spinning and revealing its hot, wounded surface with each rotation as it cooled down from the trauma. In one elegant theory, the mystery was solved. The object in the Large Magellanic Cloud was not a strange gamma-ray burst, it was the birth cry of a new field of study. We had witnessed our first Magnetar, and astronomy would never be the same. The 1979 event was a revelation, but the true demonstration of a Magnetar's power arrived a quarter century later from our own galactic backyard. On December 27, 2004, a Magnetar named SGR 180620, lurking about 50,000 light-years away in the constellation Sagittarius, woke up. It did not just flare, it detonated. For 0.2 of a second, this single object released a pulse of energy greater than the total output of our Sun over 250,000 years. It was, by an enormous margin, the brightest extrasolar event ever witnessed by humanity. Every X-ray and gamma-ray satellite in operation at the time was momentarily blinded, their sensors overwhelmed and driven into automatic shutdown to prevent permanent damage. The wave of radiation was so intense that it did something never before observed. It reflected off the moon. Satellites detected a distinct echo of the flare bouncing back from the lunar surface, a ghostly second pulse confirming the staggering intensity of the initial blast. But the most profound impact was felt right here at home. The radiation pulse, traveling for millennia, slammed into Earth's upper atmosphere. It delivered in a fraction of a second the same amount of ionization that the Sun typically produces over an entire day. The ionosphere, a delicate layer of charged particles crucial for long-distance radio communication, suddenly swelled and rippled. Shortwave radio signals were scrambled across the planet, and navigational systems experienced brief but measurable disruptions. For the first time, we had direct, undeniable proof that an object halfway across the Milky Way could reach out and physically alter our planet's environment. This was not a distant curiosity, it was a cosmic hazard making its presence known. The 2004 superflare transformed our understanding of magnetars from fascinating oddities into dominant forces of nature, capable of influencing the very habitability of planets tens of thousands of light-years away. That superflare was a message written in gamma rays, but magnetars may speak in another cosmic language entirely. This brings us to one of the most profound mysteries in modern astronomy, the enigma of fast radio bursts. Imagine a flash of radio light, a burst of pure energy that lasts only a few thousandths of a second. In that fleeting blink, it can outshine 500 million suns. For over a decade, these signals have been arriving from the distant depths of intergalactic space, billions of light-years away. Their source was completely unknown, sparking wild speculation about alien civilizations or exotic new physics. They seemed utterly random and impossibly powerful. Then, in April 2020, a clue arrived from much closer to home. Astronomers detected a fast radio burst coming from inside our own Milky Way galaxy. And it was traced directly to a known resident, the Magnetar SGR 1935 plus 2154. This was a monumental breakthrough. For the first time, we had a confirmed local source for one of these cosmic mysteries. The Magnetar did not just produce a faint whisper, it emitted a radio burst so bright that, if it had come from another galaxy, it would have fit right in with the most powerful extragalactic fast radio bursts we have seen. So how could a Magnetar create such an intense, focused radio scream? The leading theory brings us back to the starquake. When the Magnetar's crust fractures, it does not just shake the star, it sends a massive shockwave racing through the magnetosphere, that lethal bubble of twisted magnetic field lines. This shockwave plows through the sea of charged particles trapped around the star, accelerating them to near light speed in an instant. As these frenzied electrons spiral along the magnetic field lines, they emit a narrow, coherent beam of radio waves, a lighthouse flash of radiation amplified by the magnetic field's immense power. Think of it as the cosmic equivalent of a sonic boom, but for light, created in the most extreme magnetic environment imaginable. The detection from SGR 1935 was not a one-to-one match for every fast radio burst we see. Its energy was a bit lower, but it proved the principle. It showed that magnetars are capable of producing the right kind of signal in the right timescale. This single observation provided the strongest evidence yet that at least some of these mysterious signals from the deep cosmos are not messages from aliens, but the death cries of magnetic titans, their crust shattering under unbearable strain. It turned a magnetar from a fascinating monster into a potential key for unlocking one of astronomy's greatest puzzles. But this ferocious power comes with a cosmic expiration date. A magnetar's reign of terror is spectacular, yet surprisingly brief. The very engine that makes it a monster, the decay of its unimaginably strong magnetic field, is also what seals its fate. This is not a star that burns for billions of years like our Sun. Its hyperactive phase, the period when it crackles with starquakes and unleashes those devastating flares, lasts for only about 10,000 years. On the grand timeline of the cosmos, this is a fleeting blink. 10,000 years is less than a heartbeat in the life of a galaxy. Yet in that short, violent window, a magnetar lives with an intensity that few other objects can match, radiating more energy than most stars will across their entire multi-billion-year existence. During this active youth, the magnetic field is constantly stressed, twisting and snapping, fueling the star's brilliant X-ray glow and its catastrophic outburst. But this activity is unsustainable. Every flare, every burst of radiation is powered by the magnetic field's energy. With each event, the field weakens slightly, the star's internal spring unwinding. Over millennia, the relentless loss of energy takes its toll. The crust becomes less strained, the starquakes grow less frequent and less violent, and the searing X-ray glow begins to fade. The monster is slowly, inevitably running out of fuel. After its 10,000-year tantrum, the magnetar enters a long, quiet retirement. Its magnetic field, while still immensely powerful by any normal standard, has decayed to a level comparable to a more ordinary neutron star. Without that intense, twisting magnetic energy to heat its surface, the star cools dramatically. Its furious spin, already slowed by the magnetic brake, continues to gradually wind down. The frequent flares cease. What remains is a still dense, still magnetic neutron star, but one that has settled into a more predictable, quieter existence. It becomes a cosmic relic, a silent testament to a ferocious youth. So when we look out and witness a magnetar's outburst, we are catching it in a specific, fleeting moment of its life. We are seeing a cosmic teenager in the throes of its most turbulent and brilliant phase, a brief storm of creation and destruction that defines its entire legacy before fading into the dark and quiet of the galaxy. Finding these magnetic monsters requires listening to the sky in the language they speak, the searing light of X-rays and gamma rays. Astronomers hunt for them by looking for two distinct types of behavior, which we now understand are simply two faces of the same beast. The first are the soft gamma repeaters. The name says it all. These objects emit repeated bursts of lower energy gamma rays, the soft, screaming flares we have been discussing. They are the eruptive, temperamental phase of a magnetar's life, caught in the act of shattering its own crust. The second class are the anomalous X-ray pulsars. These were a puzzle for years. They are steady sources of bright X-rays that pulse with a slow, regular rhythm, but they have no visible companion star feeding them material. Their power source was a complete mystery until we realized their steady, intense glow comes from the internal heat generated by their decaying magnetic fields. Both SGRS and XPS are now united under the Magnetar model. So what are the specific fingerprints astronomers search for in the data? The first clue is the slow, heavy heartbeat. A magnetar's pulse, its rotational period, almost always falls within a very specific window between 2 and 12 seconds. That sluggish spin is a dead giveaway compared to the millisecond buzz of a typical pulsar. The second clue is erratic violence, sporadic bursting activity. Those smaller flares and occasional giant outbursts points directly to a stressed crust and a snapping magnetic field. The final, crucial piece is the sheer brightness. A magnetar's steady X-ray luminosity is simply too high to be explained by its rotation slowing down. There is no other power source visible, no partner star to steal from. The only engine powerful enough to explain that constant, fierce glow is the slow, agonizing decay of a quadrillion Gauss magnetic field. To catch these signals, we rely on eyes that can see the high-energy universe. Space-based observatories like NASA's Chandra X-ray Observatory, with its exquisite resolution, can pinpoint the faint, steady glow of a distant magnetar and measure its slow pulse. The Neil Gehrels Swift Observatory is our rapid response sentinel. Its burst alert telescope designed to instantly swing toward the sky the moment a gamma-ray flare goes off, often catching a magnetar in the act of eruption. And NASA's new STR telescope, with its ability to see the highest energy X-rays, peers into the furious processes right at the surface, studying how particles are accelerated in those twisted magnetic fields. Each new detection, each careful measurement of a slow pulse and a too bright glow, adds another magnetic titan to the map, slowly revealing where these cosmic monsters hide in the quiet dark of the galaxy. Beneath that fractured iron crust lies a reality stranger than any science fiction. To understand the heart of a magnetar, we must venture inward, layer by impossible layer. The journey begins just below the surface, in a realm where matter is compressed beyond any familiar state. Below the solid crust, the pressure becomes so immense that atomic nuclei dissolve completely. The protons and electrons are crushed together, forced to merge into a sea of neutrons. This is not a gas or a liquid as we know it. It is a neutron superfluid, a quantum substance that flows with absolutely zero friction. Picture a fluid that can never be stirred, never form a whirlpool because it has no internal resistance at all. This bizarre superfluid extends most of the way to the star's very center, and its properties are central to the magnetar's power. The superfluid can rotate independently of the solid crust above it, creating that differential motion that winds the magnetic spring to its breaking point. But the greatest mystery lies at the very core. Some theories suggest that under such extreme pressures, even the neutrons themselves may break down. They could dissolve into their most fundamental components, a soup of free quarks, and not just the ordinary up and down quarks that make up protons and neutrons, but a new, exotic form of matter made of strange quarks. This hypothetical strange matter would be the most stable, dense substance in the universe. While this remains speculative, it highlights a profound truth. The interior of a magnetar is a laboratory for physics under conditions we can never recreate on Earth. This quantum soup is the crucible where the magnetar's monstrous magnetic field was born. The process is called the dynamo theory, and it happened in the first chaotic seconds after the supernova. As the star's core collapsed, it was a churning, turbulent maelstrom of particles spinning at incredible speeds. This motion, combined with the intense heat driving convection like a pot of boiling water but on a stellar scale, acted as a natural dynamo. Think of it as a cosmic version of the dynamo on a bicycle. When you pedal, you spin a magnet inside a coil of wire, generating an electric current that powers your light. In the newborn neutron star, the rapid differential rotation and convective motions took the star's original, already strong magnetic field and amplified it exponentially. It was like taking that bicycle dynamo and connecting it to the engine of a starship. The seed field was stretched, twisted, and wound tighter and tighter by the furious motions of the electrically conductive neutron fluid. In less than a minute, this dynamo effect could boost a magnetic field 1 trillion times over, forging it into the permanent, frozen-in monster we observe today. The entire star becomes, in essence, a spinning ball of superconducting wires, a permanent magnet of cosmic proportions. The energy for those future starquakes and flares was locked into its structure in those first frantic moments of its existence, a legacy of violence written into every particle of its being. That magnetic core, forged in chaos, holds a power that could rewrite the history of worlds. The true scale of a magnetar's danger is not just in its immediate violence, but in its potential as an agent of cosmic sterilization. Picture a solar system much like our own, with a star, planets, and perhaps one world cradling a fragile atmosphere and the delicate chemistry of life. Now imagine a rogue magnetar, a solitary wanderer ejected from its own stellar nursery during its violent birth, drifting silently through the interstellar dark. Its path, by a cruel twist of cosmic fate, brings it on a close pass through this unsuspecting system. The devastation would be slow, silent, and absolute. Long before the magnetar itself entered the planetary orbits, its influence would be felt. From a distance of just a few light years, its intense particle wind and relentless X-ray glow would begin to bathe the planets. For a world with an atmosphere, this is a death sentence delivered in slow motion. The high-energy radiation would smash into the upper air, breaking apart molecules and stripping atoms away into space. Over centuries or millennia, the entire atmosphere could be eroded, leaving behind a barren, airless rock, its oceans boiled away into the void. This is not a collision, it is a slow-motion exhalation of a world's very soul, siphoned off by a passing monster. But a close pass is only one form of doom. The true apocalypse comes if the magnetar unleashes a direct flare. In our own galaxy, we have witnessed magnetars aim their fury in our general direction, their radiation washing over our planet from tens of thousands of light-years away. Now shrink that distance. Imagine a magnetar just 10 light-years away, a next-door neighbor in galactic terms, turning its magnetic pole directly toward a living world. When its crust shatters and it fires a giant flare, the planet would have no warning. In an instant, the sky would erupt in a second sun, a flash of gamma and X-rays more brilliant than its own star. The atmosphere would not just erode, it would ignite. The high-energy pulse would trigger chemical reactions, transforming the air into a toxic soup of nitrogen oxides, effectively creating a planet-wide acid bath. The ozone layer would be obliterated in minutes. Any surface life not instantly incinerated by the flash would soon perish under a relentless downpour of lethal ultraviolet radiation from its own, now unfiltered star. The planet's surface would be sterilized, its biosphere erased as thoroughly as if it had never existed. This is a hard reset on a planetary scale. Thankfully, such a cataclysm is extraordinarily unlikely. The distances between stars in our galactic neighborhood are vast, and magnetars themselves are rare. The odds of one wandering close enough to a life-bearing world and then firing a flare in precisely the right direction are astronomically small. Yet, this theoretical exercise is not mere doom-mongering. It serves a profound purpose. By contemplating these extreme scenarios, we measure the true magnitude of the forces at play. Magnetars are not just curiosities, they are natural phenomena of the highest possible energy order. Their existence reminds us that the universe is not a static, peaceful place, but a dynamic and sometimes violent arena. They are agents of change capable of sterilizing a world or, conversely, perhaps even seeding one. The same radiation that destroys complex molecules can also provide the energy to forge new, more complex ones in the nebulae they influence. Their power places them among the great sculptors of galactic ecology on a timescale of eons, reminding us that cosmic destiny can be shaped by the most furious and fleeting of beasts. The dynamo that forges a magnetar operates on principles both elegant and violent. To understand it, we must return to the first seconds after a giant star's core collapses. That newborn neutron star is not a quiet ember, it is a screaming, spinning, superheated maelstrom. It is born rotating dozens of times per second, a furious whirl that gives us the first crucial ingredient known as the Omega effect. Picture a potter's wheel spinning at a blinding speed. Now imagine that instead of clay, the wheel is spinning the star's entire interior, a fluid soup of neutrons and protons. This rapid, differential rotation where the core might spin faster than the outer layers acts like a cosmic winder. It takes any pre-existing, weak magnetic field lines and stretches them, wrapping them around and around the star's axis. This winding process amplifies the magnetic field's strength dramatically, concentrating its energy. But rotation alone does not create the monstrous, twisted fields we see in magnetars. It merely makes them stronger and organizes them in one direction. For the true magnetic monster to be born, a second ingredient is required, the alpha effect. This comes from the hellish heat inside the newborn star. In those first moments, the interior is churning with violent convection, like water boiling in a pot but on a nuclear scale. This turbulent motion is not simple up and down churning, it is helical. As hot bubbles of material rise and cooler ones sink in the star's incredibly dense fluid, the rapid rotation of the star itself, the Coriolis force, twists these motions into spirals. These helical swirls act like tiny screws, twisting the already wound magnetic field lines into complex knots and loops. The alpha effect introduces the twist while the omega effect provides the stretch. Together, in a feedback loop of unimaginable power, they create a self-sustaining dynamo. The motions generate a magnetic field, and that magnetic field, in turn, influences the motions, driving them further. In less than a minute, this alpha-omega dynamo can take a relatively ordinary stellar magnetic field and amplify it a quadrillion times, forging it permanently into the star's very structure as the fluid begins to solidify. This is the leading theory for how the universe builds its ultimate magnets. Not all neutron stars undergo this process, however. For a less magnetic pulsar, a simpler explanation often suffices, the fossil field theory. In this scenario, the neutron star is born from a star that was not spinning rapidly enough or was not hot enough internally to trigger that powerful convective dynamo. The magnetic field of the original star is simply compressed and conserved during the collapse, like taking a bar magnet and squeezing it to a fraction of its size. The field becomes immensely strong, yes, but it never reaches the magnetar's league. It remains a fossil, a relic of the star's past life, rather than a newborn monster forged in the supernova's heart. The difference lies in that chaotic, energetic birth. A magnetar is not just a collapsed star, it is a star reborn in a perfect storm of spin, heat, and motion. Its magnetic destiny sealed in a fleeting instant of cosmic alchemy. These cosmic monsters offer us something far more valuable than just spectacle. They are nature's ultimate physics laboratories, conducting experiments under conditions we could never hope to replicate. The interior of a magnetar is matter pushed to its absolute breaking point, compressed to nuclear density. This is a state where the very distinction between solid, liquid, and gas loses all meaning. We cannot create such pressures in any particle accelerator on Earth, but by observing a magnetar's behavior, we can infer the rules that govern matter in this extreme realm. Every starquake, every flicker in its X-ray glow is a message from that inaccessible core. It is a form of cosmic seismology. Just as geologists study earthquakes to map the hidden layers of our planet, astrophysicists study the oscillations of a magnetar after a crust rupture to probe its internal structure. The way the star rings, the frequencies at which it vibrates and then slowly damps out, tells us about the stiffness of its crust, the frictionless flow of the neutron superfluid beneath, and even the possible presence of that exotic quark soup at the very center. Each tremor decodes a piece of the star's hidden anatomy. The magnetic field itself is a quantum phenomenon operating on a macroscopic scale. We are observing the physics of electromagnetism pushed into a regime where it begins to interact with the very fabric of space-time, as predicted by Einstein's theory of general relativity. In a magnetar's vicinity, the magnetic field is so strong it can actually bend light, a process known as vacuum birefringence. It can even influence the properties of empty space itself, affecting how particles pop in and out of existence in the quantum vacuum. These are subtle effects, but by analyzing the precise polarization of X-rays coming from a magnetar's surface, scientists are looking for the fingerprints of this magnetic space-time warping. It is a direct test of how matter, energy, and gravity intertwine under the most severe stress the universe can muster. Furthermore, the slow spin down of a magnetar provides a pristine test of gravitational wave theory. As the star's magnetic field breaks its rotation, it should also be emitting ripples in space-time, gravitational waves at a specific frequency. While our current detectors are not yet sensitive enough to pick up this signal from individual magnetars, future observatories might listen for this cosmic hum, offering a new way to verify our understanding of these objects and the limits of relativity itself. So every time a magnetar cracks and flares, it is not merely an explosion. It is an experiment. The data from that event, the light curve, the spectrum, the oscillations, all form a complex dataset that challenges our theories. Does the matter inside behave as a perfect superfluid, or is there more friction than we predicted? Does the magnetic field decay at the rate our models suggest? Each observation helps us refine the equations that describe the fundamental forces of nature. In a very real sense, these distant, violent objects are our partners in discovery. They perform the impossible experiments, and we, from across the galaxy, carefully record the results. They force us to ask deeper questions about what matter truly is, how space and time behave under duress, and what secrets are locked within the heart of a dead star. The next time you hear about a flash from a magnetar, remember, it is more than a cosmic light show. It is a laboratory report delivered from the edge of physics, written in the language of gamma rays. That laboratory report arrives in a form we can almost hear. After the blinding flash of a giant flare fades, the magnetar does not fall silent. In the flickering X-ray afterglow, sensitive instruments sometimes pick up something remarkable, a faint, rhythmic trembling. These are quasi-periodic oscillations, or QPOS. They are not a steady pulse like the star's rotation, but a set of specific, repeating frequencies that emerge and fade, like the ringing of a bell after it has been struck. And in a very real sense, that is exactly what is happening. The colossal starquake that produced the flare did not just crack the crust, it set the entire star vibrating. These are global oscillations, the magnetar ringing like a celestial gong, but this is no ordinary bell. The vibrations are incredibly complex. Some are simple compression waves where the entire crust pulses in and out. Others are torsional oscillations where sections of the crust twist against each other, shearing back and forth like a globe with its continents slowly sliding over its molten interior. Each type of vibration has a distinct frequency, a specific musical note determined by the physical properties of the star. It is stellar seismology on a cosmic scale. Just as geologists learned about Earth's core by studying how seismic waves from earthquakes travel through our planet, astrophysicists can decode these QPO frequencies to map the hidden interior of a magnetar. The dominant frequencies tell us about the crust's thickness, Higher, fainter overtones reveal details about its density and how elastic or how stiff this iron mountain truly is. A thicker, stiffer crust will vibrate with deeper, slower notes. A thinner, more brittle crust would ring with higher pitches. By matching the observed frequencies to theoretical models, scientists can perform a remote ultrasound on a star 50,000 light-years away. They can estimate that the crust is likely about a kilometer thick, an unimaginably strong crystalline shell floating on that quantum ocean of superfluid neutrons. Every time a magnetar quakes and rings, it broadcasts a detailed sonic blueprint of its own structure. We are listening to the architecture of a monster, and each note teaches us more about the extreme states of matter that gravity can forge in the heart of a dead star. That sonic blueprint reveals a star reborn, but could a magnetar also be the architect of its own spectacular birth? For decades, the story seemed straightforward. A massive star explodes, and in the aftermath, a magnetar is left behind as a remnant, a cinder in the cosmic fireplace. But a new, radical idea has emerged, turning this sequence on its head. What if, in some cases, the magnetar is not just the result of the explosion, but the very engine that drives it? This hypothesis seeks to explain one of the most baffling phenomena in modern astronomy, the superluminous supernova. These are stellar explosions that defy all expectations. A normal supernova is brilliant, yes, outshining its host galaxy for weeks, but a superluminous supernova is something else entirely. It can be up to 100 times brighter than a typical supernova, and its light can linger for months or even years, glowing with a stubborn intensity that traditional physics cannot easily explain. Where does all that extra energy come from? The radioactive decay of heavy elements like nickel-56 can power a normal supernova's afterglow, but to achieve this level of sustained brilliance, you would need an impossible amount of radioactive material, more than the star could have possibly created. So astronomers began searching for another powerhouse, and their gaze fell upon the most energetic engine they knew, the magnetar. The theory is both simple and profound. Imagine a supernova where the collapsing core does not just form a magnetar. It forms a magnetar spinning at the absolute limit, perhaps hundreds of times per second. This newborn object is a dynamo of rotational energy. As its unimaginably strong magnetic field acts as a brake, slowing that furious spin, it converts that rotational energy into heat and light with incredible efficiency. This energy is then injected into the expanding shell of debris, the supernova ejector that was just blasted outward. It is like throwing a live power cable into a cloud of smoke, causing it to glow from within. The magnetar, buried deep at the heart of the expanding fireball, becomes a central battery, pumping energy into the wreckage for years. This sustained power source could explain the extraordinary brightness and long duration of these superluminous events. The light curve, the graph of how the supernova brightens and fades, matches the predicted slowdown of a spinning magnetar beautifully. It is a cosmic fingerprint that fits the crime scene. This idea transforms our understanding of the stellar life cycle. A magnetar is no longer merely a leftover. In these extreme cases, it becomes the active director of the spectacle, its furious birth spin dictating the entire narrative of the explosion's aftermath. It presents a universe where the corpse can reanimate the funeral pyre, shining a light so fierce it challenges our very definitions of life and death among the stars. Such a partnership seems almost impossible. A magnetar is a solitary beast, a destroyer of worlds, yet nature occasionally defies our expectations. In the vast stellar graveyard, astronomers have found a handful of magnetars not wandering alone, but locked in a gravitational dance with a companion star. These binary systems are exceptionally rare, making each one a precious cosmic laboratory. Their existence forces us to ask profound questions. Could the presence of a companion actually create a magnetar, or does it merely reveal one that was already there? The dynamics of these duos offer a unique window into how these monsters interact with their environment and whether their terrifying power can be influenced from the outside. One of the most intriguing examples is known as Swift J1822.3-1606. This system is classified as a low-mass X-ray binary. That means the Magnetar has a stellar partner, but this partner is not another giant. It is a small, lightweight star, perhaps a brown dwarf or a very low-mass star, slowly being stripped of its material by the Magnetar's immense gravity. A stream of gas from the companion star spirals inward, forming a swirling disk of superheated plasma around the magnetic Leviathan before eventually crashing onto its surface. This process is called accretion. For most neutron stars in such binaries, accretion is a predictable engine. The infalling matter carries angular momentum, acting like a cosmic whip that spins the star faster and faster, creating the millisecond pulsars we observe. But a Magnetar is a different kind of beast. Its magnetic field is so overwhelmingly powerful that it presents a colossal barrier. The accretion disk cannot easily penetrate this magnetic wall. Instead, the incoming gas is funneled along the field lines, forced to follow them like iron filings toward the magnetic poles. When that matter finally impacts the surface at the poles, it releases a torrent of X-rays, marking the Magnetar's presence. Studying a system like Swift J1822 is like watching a cosmic tug-of-war. The accretion stream tries to spin the Magnetar up, while its own monstrous magnetic field acts as a relentless brake trying to slow it down. The observed spin rate of the Magnetar is the net result of this struggle. By measuring tiny changes in its pulse period, astronomers can gauge the strength of both forces. This provides an independent check on the magnetic field strength, confirming that it is indeed in the Magnetar range, not a weaker field amplified by accretion. These binary systems are crucial for solving a fundamental puzzle. The dominant theory states that a Magnetar's field is born internally, forged in the supernova dynamo. But could a strong magnetic field also be created or significantly enhanced by external accretion over millions of years? The evidence from known Magnetar binaries suggests otherwise. In systems like Swift J1822, the companion is low mass and the accretion rate is relatively gentle. It does not seem capable of generating a field of quadrillion Gauss strength from scratch. Instead, it appears the Magnetar was born a Magnetar with its apocalyptic field intact and now simply has a small, unfortunate neighbor feeding it a meager stream of gas. The companion is not the creator but a witness and ultimately a source of fuel. This makes Magnetar binaries not factories for creating monsters but natural experiments for studying them. They show us how the most powerful magnets in the universe behave when placed in a somewhat normal stellar environment. They demonstrate that even a river of falling star stuff cannot easily tame a magnetic field born of such absolute violence. The monster remains at its core alone. 30 confirmed monsters stalk the vast expanse of our Milky Way. This is the current galactic census of Magnetars, a count of the active, flaring giants we have been able to identify through their X-ray screams and sporadic outbursts. Alongside these 30 in our home galaxy, astronomers have spotted a few more in our satellite galaxies, the Large and Small Magellanic Clouds. At first glance, this number seems vanishingly small, almost insignificant against the backdrop of hundreds of billions of stars. But this count is a profound deception. These 30 are merely the ones currently in their violent 10,000-year tantrum, the ones actively broadcasting their presence. They are the loud, awake monsters in a galaxy filled with silent, sleeping ones. Theorists, using models of stellar evolution and supernova rates, paint a very different and far more crowded picture. They estimate that our galaxy likely contains tens of millions of inactive Magnetars. These are the retired titans, objects whose magnetic fields have decayed below the threshold for dramatic flaring and whose furious spins have slowed to a near halt. They have faded into the dark, becoming nearly invisible against the stellar background, their brilliant youth now just a memory locked in their cooled, dense cores. This suggests that magnetars are not rare freaks of nature, but a standard, if fleeting, outcome of stellar death. Current models indicate that roughly 1 in every 10 massive stars that dies in a core collapse supernova may give birth to a magnetar. Think about that for a moment. In a galaxy like ours, where a star explodes roughly once or twice a century, magnetars are being forged on a regular schedule. Their active phase is so brief that we only ever see a tiny fraction of them lit up at any one time, like catching a handful of fireflies blinking in a vast, dark field, unaware of the millions of others resting in the grass. This census transforms our understanding. Magnetars are not cosmic anomalies, they are a fundamental part of the galactic ecosystem. Every one of those tens of millions of silent, dense remnants scattered throughout the Milky Way is a monument to a cataclysm, a tombstone for a giant star that died in a way so violent it twisted the very laws of magnetism into a permanent scar on the universe. They are a hidden population, a ghostly army of retired kings, their reign long past but their legacy written into the fabric of the galaxy itself. The silent majority of these retired monarchs may not stay hidden forever. A new era of observation is dawning, one equipped with tools powerful enough to listen for their faintest whispers and witness their most fleeting rages. The future of magnetar astronomy hinges on a suite of next-generation telescopes, both in space and on the ground, designed to see the high-energy universe with clarity we can barely conceive. Leading this charge is the European Space Agency's Athena, the advanced telescope for high-energy astrophysics. Scheduled for launch in the mid-2030s, Athena will be the most powerful X-ray observatory ever built. Its key instrument is an X-ray calorimeter with phenomenal spectral resolution. Think of it as moving from a standard telescope to one that can not only see the color of a distant flame, but analyze the exact chemical composition of every flicker within it. For magnetars, this is transformative. Athena will study the hotspots on their surfaces in exquisite detail, measuring the subtle shifts in X-ray light caused by atoms trapped in those quadrillion Gauss fields. It will essentially perform remote magnetic forensics, telling us precisely how the field is twisted and where it is snapping. It will also catch far more of the smaller, frequent bursts, building a statistical picture of their starquake behavior that today's telescopes, which can only watch small patches of sky, routinely miss. Complementing Athena in the future roadmap is NASA Lynx mission concept. Lynx is designed for unparalleled sensitivity and imaging resolution in the X-ray band. Its goal is to see the faint, the distant, and the fast. Lynx will be able to detect the X-ray afterglows of magnetar flares from the very edge of the observable universe, tracing the population of these objects across cosmic time. More importantly, it could capture the initial milliseconds of a giant flare with incredible fidelity. Currently, when a flare goes off, our satellites are often blinded, and we miss the crucial first moments of the explosion. Lynx's advanced detectors are being designed to handle that extreme flux, allowing us to watch the starquake itself unfold in real time, frame by terrifying frame. This data would be the ultimate test of our models, showing us exactly how the crust fractures and how energy propagates through the star's interior. While space-based eyes peer at the X-ray fury, a colossal ear on the ground will listen for the radio echoes. The Square Kilometre Array, or SKA, is not a single telescope but a vast network of radio dishes and antennas spread across South Africa and Australia. When its first phase is completed in the late 2020s, it will be the most sensitive radio observatory in history. The SKA will conduct a continuous, all-sky monitor for fast radio bursts, catching thousands of them and pinpointing their locations with exquisite accuracy. Every time a galactic magnetar like SGR 1935 plus 2154 burps out a radio burst, the SK will hear it with crystal clarity. By comparing the detailed properties of these local, known magnetar bursts with the mysterious ones from other galaxies, scientists hope to finally confirm once and for all that magnetars are the dominant source of these cosmic sirens. The SK could also detect the faint, steady radio pulsations from older, quieter magnetars, those retired titans we currently cannot see, finally taking a census of that hidden population. Together, these missions form a perfect triad of perception. Athena will dissect the physics of the magnetic field itself. Lynx will capture the explosive anatomy of the flares. And the square-kilometer array will map their radio voices across the cosmos. This coordinated assault will transform magnetars from enigmatic monsters into open books. We will move from catching rare, dramatic outbursts to understanding their daily lives, their life cycles, and their ultimate role in shaping the energetic tapestry of the universe. The data they return may not just solve existing puzzles about extreme matter and fast radio bursts. It will undoubtedly present new, deeper mysteries we cannot yet imagine. The golden age of magnetar science is not behind us, it is just about to begin. Their legacy is written not just in light, but in the very atoms that build new worlds. The supernova explosion that forges a magnetar is a cosmic foundry of the highest order. In its furious heart, temperatures and pressures soar to levels that fuse lighter elements into heavier ones, far beyond the iron that signaled the star's demise. This rapid neutron capture process, the R process, creates a rich spectrum of the heaviest elements in the universe, including gold, platinum, and uranium. The cataclysm then blasts this freshly forged material into the surrounding interstellar medium, seeding vast clouds of gas and dust with the raw ingredients for future planets and potentially life. Every magnetar's birth is therefore an act of creation as much as destruction, scattering the elements of future complexity across the galaxy. Its influence continues long after the initial fireball fades. The expanding supernova remnant, glowing for thousands of years, and the magnetar's own relentless particle wind and radiation create a powerful shockwave that plows into neighboring molecular clouds. This compression can trigger the collapse of dense pockets within those clouds, catalyzing the birth of a new generation of stars. In this way, a magnetar becomes a reluctant midwife, its death throes helping to spark the beginnings of new stellar systems, some of which may one day form rocky worlds with their own chemical richness. As a population, these magnetic titans are integral to the galactic cycle of death and rebirth. While any single magnetar's active phase is a brief flash, the continuous production of them over the Milky Way's long history means their combined effects are profound. They contribute to the chemical evolution of the galaxy, gradually enriching it with heavy elements across eons. Their energetic outputs help regulate the temperature and turbulence of the interstellar medium, influencing the rate and efficiency of star formation on a grand scale. They are not mere outliers, but key agents in the ecosystem, their extreme physics leaving a permanent imprint on the galactic environment. Ultimately, studying magnetars helps us map the divergent fates of massive stars. They represent one possible endpoint in a stellar spectrum of corpses. A star's final form, whether it becomes a white dwarf, a neutron star, a magnetar, or a black hole, depends on a delicate balance of its initial mass, spin, and magnetic field. Magnetars show us that magnetism is a dominant force in this cosmic decision-making. They sit at a critical threshold, a demonstration of how a slightly faster spin or a different internal dynamo can tip the scales from creating a normal neutron star to birthing a magnetic monster. By understanding them, we better understand the entire menagerie of compact objects that lurk in the dark, from the silent black holes to the steady pulsars. They remind us that the universe favors diversity, even in death, and that the most violent events often hold the keys to its grandest cycles of creation. That chemical legacy is profound, yet the most pressing question remains: Could one of these magnetic monsters ever turn its fury toward our own world? The answer lies in the cold, hard math of interstellar space. The nearest known magnetar to Earth is called XTEJ 1810-197, and it sits approximately 8,000 light-years away. At that staggering distance, its influence is reduced to a scientific curiosity. Even if it were to unleash a full giant flare directly along our line of sight, the effect here would be dramatic but not destructive. Our satellites would register a brilliant flash in the gamma-ray sky, perhaps suffering temporary instrument overloads as they did in 2004. Astronomers would witness a historic event, a chance to study the physics of a starquake in real time. But for life on the surface of Earth, it would pass largely unnoticed. The atmosphere would shield us from the worst of the radiation, just as it does from most solar flares. We would be perfectly safe spectators to a cataclysm halfway across our galaxy. This safety is a gift of cosmic geography, not a guarantee of the object's nature. To understand the true threat, we must shrink that distance, bring a magnetar to within just 10 light-years of our solar system, a next-door neighbor in galactic terms. Now, if its pole were aimed at us during a crust rupture, the scenario changes utterly. The initial flash of gamma and X-rays would arrive without warning, traveling at the speed of light. It would deliver, in milliseconds, a radiation dose equivalent to thousands of years of our sun's total output. The upper atmosphere would be violently ionized, generating a thick smog of nitrogen oxides that would blot out the sun and fall as acid rain. The planet's protective ozone layer would be obliterated in an instant. Any complex life on the daylight side of Earth would face instant sterilization from the radiation pulse, while the ensuing years would see a collapse of the food chain under a relentless barrage of solar ultraviolet radiation, now unfiltered. It would be an extinction-level event, a hard reset for the biosphere. This terrifying exercise is not a prediction but a measurement. By running these calculations, we are not forecasting doom. We are using the hypothetical to calibrate the sheer magnitude of the forces involved. The fact that such an event is extraordinarily unlikely, given the vast emptiness between stars and the rarity of magnetars themselves, highlights a profound truth. We inhabit a quiet, stable backwater in an otherwise dynamic and often violent galaxy. Our local neighborhood lacks the stellar density and recent supernova activity that would place such an energetic remnant nearby. This cosmic serenity is what has allowed life on Earth the eons of stability needed to evolve and flourish. So, while we can watch these distant monsters crack and flare with awe, we do so from a balcony seat so far removed that their roars reach us as whispers. Our study of them, then, becomes a study of our own good fortune, a reminder that the universe's most furious artists are best appreciated from a very, very long distance. The universe's most powerful magnets are not built, they are forged in violence. Each magnetar is a testament to a star's catastrophic death, its core collapsing into a sphere of nuclear density where a magnetic field a quadrillion times stronger than Earth becomes frozen into its very structure. This is not a static force but a living, writhing entity. It strains the star's iron crust until it shatters in a starquake, unleashing a flare of energy that can outshine our sun for 100,000 years, a scream felt from another galaxy. These events are not mere spectacle, they are cosmic puzzles. The same magnetic fury may power the mysterious fast radio bursts that echo from the deep cosmos, and a newborn magnetar's spin could be the hidden engine behind the most brilliant superluminous supernova ever seen. To study a magnetar is to probe the absolute limits of physics, to ask what matter becomes when crushed beyond recognition, and how space-time itself bends under the weight of pure magnetic will. These monsters remind us that the universe operates on a scale of power and beauty far beyond our everyday experience, in realms where the rules are written in gamma rays and gravitational waves. Their existence challenges our understanding and expands the frontiers of what we know is possible. What aspect of these magnetic titans strikes you as the most terrifying or the most fascinating? Is it the idea of a star tearing itself apart, or the thought of a magnetic field so strong it warps reality? Share your thoughts in the comments below, and if you enjoyed this journey to the edge of cosmic physics, be sure to like and subscribe for more explorations into the universe's deepest mysteries.